Peter here to talk about PCB back drilling. I hope you're all excited as I am, because today I've got a special guest for you. As we go along, ask your questions in the Q&A box. Please don't use chat. All right, my favorite Royal Circuits and Solutions employee, Elijah Gracia, a senior CAM engineer. Elijah, tell us a little bit about yourself.
Hey, Mark. Yeah, thanks for having me. I've been a CAM engineer here at Royal Circuits for the last 6 years. Basically, I work on all the DFM, DRC checks for the orders that come in and get them all ready for the shop.
All right. Can you tell us a little bit about the shop? Royal Circuits, I believe, has been around for, we've been around 15 years now?
Yeah, we've been around a little bit longer than 15 years, but we specialize in quick turn prototypes. We are one of the fastest shops that I've ever heard of. We can get stuff done pretty darn quickly. I think our fastest job was about half a day, actually. And yeah, pretty cool.
Yeah, finishing jobs from order, from taking the credit card to out the door in a single shift is a pretty impressive feat. I imagine it was also a pretty big credit card.
Oh, yes, definitely.
All right, so we wanted to talk about back drilling, and for the uninitiated, and I really can't imagine there's that many people on this webinar who don't know this already, but anytime that you have an impedance discontinuity, a signal that goes down and reaches that discontinuity, it's going to have some energy reflected. And that degrades the signal and also creates unwanted noise. It's a no bueno in PCB design. Now, we oftentimes, as design engineers, have to change layers. We really don't have a choice. If you have two things that are going to cross, you can't let them do it. It's a short circuit, so you have to drop down a layer. Or if you're trying to prevent unwanted electromagnetic distortion or interference, you sometimes will have to drop a signal down into a midplane layer and put some ground on either side just to contain it in the board. Well, the issue comes up in that as you go down to a lower layer, if you created a through-hole via that goes through the full length of your board, that stub, that little extra bit of copper, can cause a lot of troubles. Let me see if I can get a pointer on here and I'll describe why. Oh, laser pointer. All right. So we have a signal that comes in on the bottom layer, transfers to the top. Well, hopefully you're able to design your via in such a way that the impedance discontinuity isn't all that great. And also hopefully if you're lucky, you've got a nice thin board, it's electrically short, you don't have to worry about it. But as long as the impedances are kind of close to each other, and maybe you can do better than 70, I just wanted to make up a couple numbers, you're not going to get that much reflection. If you can somehow make your via, the same as your trace, you're going to get no reflections. Although, practically that never really happens. But you go all the way down to the edge of the board with that via, and suddenly you go from whatever the impedance of your via is to the impedance of free space, of error. It's going to be a little less than 377 ohms. Well, that's a big difference, right? 70 to 377 versus 70 to 50, big problem. So then the question is, well, why do you use a through-hole via? And the answer is because those are the cheapest vias that you can possibly make into a board. So one of the solutions that we have, if that is going to cause noise, reflections, ringing in your design, we can actually go in with a drill and delete that. But you have to be very careful on how deep you drill, otherwise you can disconnect the trace. And if you don't drill deep enough, you still have the stub left behind. So what that does in your design is it starts to close your eye. We've got an eye diagram that I borrowed from a paper I found online here. And what these things do are, the logic transitions. The eye diagram shows you, the 0, 1, 0 transitions. 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1. Right? All of these possible logic transitions that might take place. And if this gets closed in either the vertical or the horizontal direction, your receiver is no longer able to really figure out what logic levels are what, and you're unable to transmit data. So these stubs put in these little horizontal pedestals. So instead of having these smooth transitions, the stub lets the signal start to drag out. You start getting these other intermediate logic states. Again, as long as you have the eye open, you can usually figure out what's going on. But if you design in such a way that that eye closes, then you're out of luck. The length of the stub matters, and how much you can get away with depends on the frequency of your transmission. For 6.25 gigabit, and again, this is that paper that I sourced earlier, kind of shows you how much of a stub that you can have and you're still going to get signal. Maybe you aim 4, 5, or 10 mils. You're not going to lose that much signal. You might get a little bit more noise, but you also might get away with it. All right. Who's going to care about this webinar? Well, it depends. If you guys are going faster than, roughly 10 gigabits per second, or you've got some crazy low bit error rate, you're probably okay with a 10 mil stub. But other than that, if you are going faster than 10 gigs, you're probably going to have back drilling if you have through-hole designs. Next. All right, Elijah, that's kind of the background. Now, can we start harassing you and have you tell us everything there is to know about PCB design?
Yeah, definitely. So just to give you some background, that way you can better understand what we're doing with the back drill. Right here, we're looking at one of our travelers. This is the cover page. That's the very first start of your job once it's all been run through DFM and DRC. So basically what a stack up is, it's the sandwich that we're making to build your board. Stack up and construction technique determine the via construction. There's a lot of different ways we can build your boards. And we want to go over a couple of ways that we can do that today. So some of your stack up options are going to be foil and cap. So if you look on the left side, the top and bottom layer are just a solid sheet of foil. And you're going to have a core with layer 2 and 3 right in the middle. So that's the easiest way for our shop to build your board. We prefer that so much more than cap. But if your board requires it, we do offer cap construction on the right side, which is, you can see there's a core on top, which is layer 1 and 2, separated by prepreg, and then layer 3 and 4 on below that.
So why would a designer call out cap versus foil construction? Foil is easier for you guys to design.
One of the common reasons we get cap would be a hybrid construction where maybe they're using a Rogers material on top and a regular 370 material on the bottom. Okay,
so a high-speed designer might have to do this. They might need a cap construction.
Correct.
All right. But with a foil construction, couldn't I just do micro vias and build this stuff up so I don't have anything that needs back drilling?
Absolutely.
Okay, so that might be the cheaper way to go. So you like building the foil better, and
yes.
I could potentially just do micro vias and not have to worry about any of this.
Correct. Yeah, we're always going to take a look at your design and the stack up and make it the best, what's best for us, the easiest for us, and also the cheapest for you.
All right. So Elijah, can you tell us a little bit about the different types of vias you guys can make and how you make them?
Yeah, of course. So if we start on the left side, we have the buried via. And the way we do that, that's a via that doesn't reach the top or the bottom. It's buried inside of your board. And the way we do that is we're going to start with a core in the middle. We're going to drill and plate through it. And then we're going to build the rest of the sandwich on top of that. And so what you end up with is a buried via.
Okay, and no stub, so no problem, right?
Correct. The other way we do that would be a blind, which is when the hole goes through one side but not the other. It doesn't penetrate all the way through the board. And that's basically done by creating the core, drilling it same way, and then when we do the next lam, we're going to laser drill the next portion of that, and that's how you'll get blind vias.
Okay.
The next one's through hole. That's your standard hole. That's a hole that's being drilled all the way through. You can see it's got some connections going through different layers, but nothing special. Easiest way we can do a hole.
Real quick, there's a story that you told me a few months back about a customer that had some buried vias in their design that you talked them out of. Can you share that with us real quick?
Yeah, definitely. Customer had a pretty huge order. I think it was a couple thousand pieces of a pretty large board, and they had some blind and buried vias going all the way through it. And when we took a look at their design, there wasn't very many holes. So we thought, okay, maybe there's a cheaper way of doing this. Maybe we can do like a epoxy fill, which is a little bit cheaper option. And after talking to the customer, we realized that they didn't actually need a blind or epoxy fill, that we were actually able to move a couple through holes, and in the long run, it saved them about 50 grand.
Wow. All right. How about our laser form vias now?
Yeah, so laser form, perfect. So the way we're going to do this stacked vias, that's when you're working with tighter spacing. What we're going to do is start with the very center core. We're going to drill it, plate it, and what we're going to do next is add the next layer on top and bottom of that. We're going to laminate it, make a new sandwich, and then we're going to get a laser drill down to that next layer, and we're going to keep doing that over and over, as many layers as you need it to go. So as you can see, this one's going to be laminated about 4 times, and it's going to create that stacked via.
And I see I could have done a little better on those vias there. It looks like I've got a different number of stacked and staggered. Sorry about that.
Oh, that's okay. And then the staggered is essentially the exact same thing, but that's when you've got some really tight space and you can't quite get your holes right on top of each other and you're really pushing for that extra space. That's when we'll go with the staggered vias.
Wow. All right. So these we would see on either a cap or a foil design, but we would really only see the laser form vias on a foil design, right?
Correct.
Okay. So we can avoid worrying about back drilling and all that other nonsense, potentially by how we create, what vias we choose to begin with. However, it's more expensive to do a buried via than it is, say, a back drill via. Is that what I'm hearing?
Yeah, definitely.
Okay. All right, let's do quickly, how these mechanical vias are formed, if you don't mind.
Yeah, definitely. So I know we got some different level of builders out here. So really quick, the basic way that we make a via, you start on the very far left with a solid sheet of material. And that's just a piece of copper on top and copper on bottom that's already been laminated. First thing we're going to do is drill a hole. After that, we're going to apply the dry film. And what that's doing is leaving the exposed area so that we can now plate a barrel down through that hole. So what we're going to do now is go to our electroplating process, and it's going to put copper in the hole and build it up on top and bottom layers. Then we're going to strip off that solder mat or that dry film layer. And the very last step is we're going to etch it down a little bit, which is going to take just a hair off the top and get rid of all that extra copper we need. And that's going to leave us with the design that you're asking us for.
All right, so all of my mechanical vias are made in essentially that process. And then if you laminate other layers on, you can end up with a buried via. Or if you add perhaps a laser drill, you can get a blind, right?
Correct.
Okay, I think I'm following along. So one of the things that surprised me is that core and pre-preg are pretty different stuff. Core, it sounds like there's usually a whole lot more fiberglass and a whole lot less epoxy, just because you're laminating 2 full sheets of copper together. Pre-preg, however, has a ton more epoxy, so there's a lot more variation in design. So as a designer, I would expect better signal integrity using core than pre-preg, right?
Right. Yeah, that's what's going to happen when you're because the core has already been laminated. Some of that resin's already been pushed out of the edges. Whereas the prepreg still needs to be laminated to kind of, I guess, put the sandwich together. So we're going to need that resin to help us out.
So can you tell us then, why is it that you prefer foil over cap construction? Does it have to do with what happens with all that prepreg and, you know, the copper traces rolling, or what's the preference there?
Somewhat, yeah, it has to do with the prepreg and cores. What it mainly comes down to is registration. It's a lot easier for us to get a solid registration out of a foil construction.
Okay, so to get everything lined up is the issue.
Yeah.
Okay. All right. Let's get the next slide going there. So how important is a balanced stack up in the fabrication process?
Super important. Basically, what we're talking about here is a balanced stack up. If you're looking on the right side, if we cut that right down the middle, the top side is going to mirror the bottom side. And what that is doing is keeping a nice even board, where if you look to the left side, it looks like we've got layer 1, 2, and 3 pretty tight together on the top half. And between layer 3 and 4, we got a pretty large section of core material. What that's going to do is that bottom piece is going to be a lot stronger than the top, and it's going to start to bend the top side. It's going to give into it. So you're going to get an unbalanced stack up, and that image right below it is perfect. It's what we call potato chipping. That's what your board's going to look like, essentially. It's going to start to bow and bend and want to pull different ways. And we don't like that. Your assembly shop's not going to like that, and we want to keep your board as flat as possible.
So I imagine that when you laminate boards together that, I mean, you know, let's say we want a 62 mil board. Is it really 62 mils, you know, planar surfaces, or are there slight variations as you go around?
There are slight variations depending on what copper weight you're using, but our stack up calculator, we try to get as close as we can to your finished required thickness, and our standard shop tolerance is going to be plus or minus 10%. That's just kind of an industry standard.
Okay. So real quick, and you may or may not know the answer to this, I don't know, but these pictures on the left, those are actual scale thicknesses from customer projects. The pictures on the right I just made up, but the pictures on the left, I actually got these, the travelers from Omar, I think it was, or Teresa, I don't really remember.
Right.
So why do you think engineers use unbalanced stack ups?
From what I've seen, a big deal is they'll have different impedance structures from top to bottom.
Okay.
Sometimes it's not possible to get it with a solid balanced stack up. So we'll kind of, we have a little bit of tolerance where we can create an unbalanced stack up. And in some cases, a customer can approve a little bit of warpage.
Are there any advantages to unbalanced stack ups, or is it just a consequence of other engineering decisions?
Yeah, just a consequence. I can't think of a single advantage an unbalanced stack up would have other than being able to achieve your unbalanced impedance models you might have.
Yeah, I don't know either. So, but you should always aim for balance whenever you can. And here's something else to keep in account too for you designers out there. We like taking copper off boards as designers, right? That's how we route traces. The boards come as sheets of copper. They have to be etched to remove that copper. Well, we sometimes get into the habit of running vertical traces on one layer and then horizontal traces on an adjacent layer, just to minimize the crosstalk. Well, you've now unintentionally created an unbalanced stack up. The thing that causes the warpage are differential coefficients of thermal expansion between the copper and the laminate material. The laminate will expand much more than the copper will. So if you take a look at this picture, we've constrained the expansion in one direction on this layer, and on the bottom, we've constrained it in another direction. There's the same amount of copper, there's still 50% coverage on each board, but not 50% in the same direction. So you can sometimes create this warpage unintentionally. Even if you do start with a balanced stack up by the way that you route your traces. So just one more thing to worry about. So I guess my next question is, how do I, let's say I need back drilling. How do I call this out for you guys? How do you do it?
Yeah, so first thing we're gonna request is that you have separate drill files for each depth. Say you have 2 different depths that you want to do on your back drill, like that image on the bottom right. You're gonna want 2 different files so that we know which size you're trying to get from layer 1 to 5 and which one you're going from layer 1 to 11. That helps us keep track. That helps us just be a little bit more organized and avoids any confusion. The other thing we're going to want to hopefully see is on your README or fab print, let us know, just a simple note that says, hey, there's 2 controlled depth drill files. I have a maximum stub length of 10 mils or whatever you're requesting. Just a quick little note, and if you can add an image like the one where the laser pointer's at, that is perfect for us. It avoids all confusion. Another good thing to add in, if you see on the 2 left portions right there, that note's saying very easy, this is controlled depth drill file, 1 of 2, and that bottom layer, or that second line is perfect. Drill layer 1 through 11, do not cut 12. That's telling us exactly how far we should be going. We want to cut all the way from layer 1 to 11, and we know not to hit layer 12. That's going to cause some problems. Simple notes like that, it avoids all confusion and makes it really easy for us.
Yeah, because if there is any confusion, you guys aren't going to run the job, right?
Correct. We're going to stop it, put it on hold, and we hate doing that. We like to get your jobs through the shop. We like to not bother you if we don't have to.
All right. As far as modifying the drill files, these are the first lines of drill files that I just invented. It's fine to add comments to those, correct? Or do you know?
You're talking about adding these 2 lines in a drill file?
Yeah, adding these 2 comments. Do you guys see those, or is README better? What's the best way to do it?
README's fine, or you can also add them to the drill file as long as you have a semicolon at the beginning.
All right. Joining us in the background is another one of our expert engineers, Matt. Welcome. Thank you for coming. Is there anything you'd like to add in, Matt, on drills? What a designer can do to make things cheaper, better, faster, easier?
Well, each back drill segment you have is going to add more money, so the fewer the better as far as money goes for you. The more the better for us because it's more money. We prefer the original primary drill plus 10 for the back drill diameter. We can go smaller than that if necessary. And that's about it.
Okay, so the original drill file plus 10 mil diameter,
Yep.
is what you said?
Yeah, that's the most common.
Okay. All right. Well, with that, I think we might be ready for a few questions. A nice short webinar today. All right, first one. Some RF designs require different decay and the boards may be unbalanced or could have odd layer counts. Does this present a problem?
No, I actually tooled the job this morning with an odd layer count. We had 9 layers instead of 10. So technically it was unbalanced, but because the customer gave us the option on how to build the stack up, we were able to still balance it out. We're able to still use that wiggle room and get a balanced stack up for you. So no.
And we've got a, what is that thing, like a 40-ton press?
More than that.
More than that. I mean, we've got a huge, huge press. And we've got some smart engineers. We can flatten out your board. But the issue that you might run into comes in assembly when that board gets heated back up for, to melt the solder paste. It might warp on you then. And you can't put flat parts on a bent board. So it's always just something to keep in mind and work on when you can. All right.
Yeah. Just to add on to that, we do have stack up engineers. If you have any questions, go ahead and contact them. And then they can help you out in figuring out a way to get a balanced stack up where you can't quite figure it out.
Absolutely, and that is a free service you can do at the very beginning of your project, even before you put down your first trace in your design program. Just contact us, let us know what you're doing. We'll help you out. All right, this one might get into some proprietary information, but the question is, what tolerance can you hold? I hear silence.
He's asking what tolerance can you hold?
Plus or minus 5 on the stub length is the most common.
Okay, so it comes down to cost, right? The smaller that you want us to make that stub, the more risk is involved, the more time it's going to take to do it, so the more we're going to charge you for it. So Matt, if you weren't able to hear him, said plus or minus 5 is a pretty common call out for your design. And we've got some new machines in the dock right now that are going to be installed that can improve on that number too. So that might not be a standard much longer. Okay, question is, as far as reliability goes, what is better, staggered or stacked microvias? Or are they about the same?
Staggered.
Staggered is the is what's called out in, and I forget which document, but staggered usually is because you know you're going to be hitting good clean copper. It really comes down to the the plating and how well that copper goes in the hole, how flat they can get it. If you just move off to the side a little bit, you know you're getting good clean copper to make that next attachment point. That being said, if we were to microsection your cell phone right now, we would probably see stacked microvias, 12 layers deep. Anyhow, microvias, if you guys suspect failure on once a board is fully assembled, can you x-ray those? How do you find out? Do you have to do destructive testing with microsections, or can we do non-destructive?
I think cross-section would be our easiest way, cheapest way. Just cut the board up and see what's going on.
Can we x-ray that small and see suspect failures, or would they not be visible?
No, they wouldn't be visible.
Okay, so unfortunately right now we've got destructive means of investigation, but we do that. So Fred asks, at what point in the process is back drilling done?
Usually, well, not usually, sometimes it's done prior to via fill if there is a via in pad associated with that hole on one side of the board or the other. More commonly is just prior to electrical test. So after all the plating and etching operations have been done.
Okay, so at the very, very end then. All right. Question, does an odd number layer count board cost more than an even layer count board?
No difference.
Well, that was easy.
Yeah, on our side, we still kind of build it as an even layer board, theoretically. It's just we etch off copper in one of those cores.
All right. Question is, what's the best option for via in pad, laser or mechanical? So a VIPO, I'm guessing they're asking a VIPO via in pad plated over.
If you do not need the blind vias, then through hole with epoxy fill would be the best and cheapest.
Okay. Is going back to vias stacked versus staggered, is one more expensive than the other?
No.
All right. Is there a big cost difference between blind laser drills versus back drilling?
The back drill is less expensive.
Okay. So next question. If you support plus or minus Z depth tolerance on drills, what's the locational tolerance? So what's the XY?
Are we talking about a back drill? What are we?
Okay, so let me read the question in its entirety, and then I think we're just going to have to best guess it. If you support plus or minus 5 tolerance on drill depth, what is locational tolerance? I would assume we need to consider this in any plane clearances as well. Seems like 10 over will grow our clearance holes. So I think what they're worried about is, if we are doing back drilling, how much space do we need to leave for like an anti-pad, an airspace, so that we don't short out stuff?
Yeah, probably plus or minus 3 would be probably a worst case on the hole location.
Okay, so we can hit it closer than 3 mils. But what about how big of a airspace hole do I need to leave on my other plane, my other layers?
An additional 3. So
13 mils instead of the 10. Right? So so let's do some sample numbers. I've got a 10 mil drill, and then I'm going to back drill. So I'm going to use a 20 mil diameter back drill, and I'm going to have a 23 mil diameter airspace and an anti-pad on the other layers. Is that accurate?
yeah, sounds accurate.
Okay. All right, I hope that helps. If not, shoot me an email at mhughes@royalcircuits.com, and I'll see if I can't come up with a diagram for you. Les, if you could, I've just got one that says less dish, and I'm afraid I don't know what you're asking there. So maybe if you could help me out with that, I can help you. Question is, do customers always require epoxy fill of back drilled holes or not? And if not, why not?
Sometimes we back drill holes that are located where there's press pit connector, so you could not do via fill on those. And if the board does not have via and pad and does not require via fill, then you would not want to via fill because it's extra money.
Okay. Any other questions out there? We would be happy to answer. We'll give you just a minute for that. While we're waiting, I would like to let you know that Elijah and I will be speaking at PCB West next week, in fact. So if you have some time, I believe we're Thursday morning at about 8 or 9 o'clock. We've got a 90-minute presentation for you on PCB fabrication. It should be pretty good. All right, another question. Wouldn't the anti-pad for a 20 mil back drill with a plus or minus 3 mil tolerance be 26, not 23 mil diameter? So Matt, so you said that the XY was the worst case scenario is 3 mils, but we actually can do much better than that, right?
Yeah.
Okay, so the question is, did I do my math wrong? And it sounds to me like I did. Shouldn't it be 26 mil? So we've got a 10 mil via, 20 mil back drill. Do I need a 23 mil diameter or a 26 mil diameter hole to stay away from the edge?
It sounds like 26 without having,
Okay. Yeah, and Tom, I think that's right. I think I was just doing it off the cuff and I did it wrong and my board would fail and I lose money. Ah! Hey, do we locate these things with X-ray machines when we're trying to back drill? How do we do it?
we use vision.
Okay. All right. Any other questions? Then with that, I really want to thank Elijah and Matt for joining us on an unexpected surprise. So thanks for jumping in there, Matt. If you have any more questions about back drilling, please feel free to email Elijah@royalcircuits.com or contact me at mhughes@royalcircuits.com, and we'll help you follow up. This webinar has been recorded and it will be posted on our YouTube channel within a couple days. If you would like the slides, you can find those at royalcircuits.com/blog as soon as we're done editing the video. Thank you so much. I hope you found it useful. It's a little shorter than our typical webinars, but it was fun. So thanks, everyone. Have a great rest of the day, and bye.